All right, thank you, Scott, and thanks all for coming out. I'm really pleased to be here today. Maybe I'll start with a question, just by show of hands. How many of you have walked along the waterfront here in San Francisco, as shown in the photo? Just to check if you're paying attention. I assume everybody's been up there. All right, it's a beautiful space. People come from around the world to visit the city and walk along the water. It's a transport corridor for tens of thousands of people every day. It's an integral part of many neighborhoods in the city. But it's also facing a lot of risk from a variety of types of disasters, and those are the types of problems that I think about with my work. So today I want to come and tell you a little bit about the types of methods we use to think about these problems, and hopefully make an ask that some of you might be able to engage with this work through your own expertise, and I'll try to make a pitch for how that could work. So speaking of the risks for this, the seawall in San Francisco, thinking particularly about that waterfront area. All right, so this is a not too unusual photo these days. A couple times a year at king tide levels, we see this moderate flooding as the water elevations are reaching about the road level. This problem is obviously going to get a lot worse in the coming decades. I think San Francisco's waterfront is unique in many ways, but the challenges facing coastal communities, of course, are going to be shared around the world. Additionally, many of you probably know that the waterfront of San Francisco is not the natural waterfront that was there hundreds of years ago. That during the gold rush, there was a lot of fill dumped in along the shoreline to create additional land. That material is not very well compacted, and during earthquake shaking, it's very susceptible to settlement and lateral spreading. This is that same waterfront area. This is a famous photo from the 1906 San Francisco earthquake, where a lot of the material along the waterfront spread out. It tried to move downhill, which means move out into the bay. That same soil is sitting there today, so the same types of problems could happen, except now there's many, hundreds of thousands more people, billions of dollars of assets sitting right behind that wall, and billions of dollars of infrastructure buried underneath the roadway there as well. Right? And these systems, I find them they're fascinating because they're vibrant, critical parts of our societies, and they bring richness to life. Each one of them is unique. Each one of them is designed to be very long-lived, right? A lot of the systems that are in place there are more than a century old. We need to do things about them, but we have to be careful when we do those things, because if we get it wrong, we don't get to just push a software update and fix it, right? We get one chance to fix these systems, and we're designing them for conditions we haven't yet seen. So all of those creates a lot of challenges and a lot of interesting problems for us to research. I should note, if those of you that have been following, so this is, right, the problems here are not news. This has been under study for many years. The San Francisco Chronicle's had a pretty good series of articles talking about the challenges and the potential solutions to it. The most recent article just came out last week discussing what's ultimately going to be a multi-decade long project that's going to cost $10 billion or more to revitalize the waterfront and protect it from these challenges in the coming decades and centuries. This is another place that I think a lot about in my work. This is Christchurch, New Zealand, circa 2016. So I spent the year of 2016 in New Zealand, in Christchurch, on my last sabbatical. And a large earthquake struck under the city a few years prior to this. The building stock did pretty admirably, for the most part, in protecting the occupants of the buildings. There were a couple really tragic collapses, but there was not a heavy level of fatality such as we see in some other parts of the world in earthquakes. But this is what the downtown looked like 3 or 4 years after the earthquake. All of those bare spots you see all over the photo, there used to be buildings there in a more vibrant central business district. Most of them were torn down for economic reasons, as the building owners were incentivized for various reasons to decide that the best path forward was to just tear down the building, wait a little time, and maybe rebuild. This created, obviously, a tremendous amount of disruption for the city as it tried to operate, for the residents of the city. And it created a lot of uncertainty in the recovery process as people were waiting for each other to move first and kind of come back down to the downtown area. And so the drivers of kind of economic and social factors, rather than only safety factors in this process, were really striking to see them firsthand. Another thing that was striking to see firsthand there, this is another neighborhood in Christchurch out a little bit towards the coast. You can see the Pacific Ocean there in the background. And this, before the earthquake, was a residential community. It was low-lying and somewhat flood-prone, but again, the earthquake here caused poorly consolidated materials to settle pretty substantially, and what was a somewhat risky neighborhood before the earthquake became untenable due to the flood risk primarily after the earthquake. After some kind of a lot of struggle, the city decided that it just wasn't viable to provide infrastructure services there or to rebuild housing there. And ultimately, 10,000 people were relocated out of this region to other parts of the country. And I think in a very short time span that this earthquake accelerated, to me, it gave a glimpse of what sea level rise and managed retreat is going to look like. And even in a relatively well-to-do community, in a high functioning government, it was an incredibly painful and disruptive process for the community. And so, thinking about this and thinking about how we design our communities and our built environments really drives a lot of my research. And a couple of problems I want to talk about today. One is, how do we design for resilience, right? How do we keep design so that our cities can bounce back from these extreme events and our communities can thrive and the residents of those communities can thrive and live their best life? And then two is, how do we design for a future that's unlike the past? This is a little bit of a different paradigm for the way in which these large, long-lived systems are designed and managed, and it's forcing some reckoning with the way that we do business as usual. So first, this resilience problem. And so I mentioned already that in Christchurch, those buildings they protected occupant safety. And maybe some news to some of you, that's really what our regulatory environment here in the US and most of the country, or most of the world, aspires to occupant safety in extreme events. So the goal is that you and I, when we walk into this building, we have an expectation that we're not putting our safety at risk, or we're not putting our lives at risk by being inside of a building, even if an extreme event were to occur. And so regulations are in place to ensure our safety, right? And this involves things like fire exits and smoke detectors, but also structural systems so that buildings don't fall down in earthquakes. But by that metric, these buildings here are successes. These are a couple buildings that were damaged in recent California earthquakes. They protected the occupants, they got out okay. And that's something to be celebrated, right? That much of the world hasn't yet gotten to that level of performance, so I don't mean to minimize that. But people are displaced from their homes in those structures. Businesses are closed. If those buildings have to be torn down and replaced, it's a tremendous amount of waste and carbon impact. And so we've come to realize this is really not a success story, and that regulations should not just be satisfied with this level of performance. The field of civil engineering in the past couple decades has really moved towards greater aspirations and thinking about disaster resilience. So the top photo is of a government building in Oregon that opened a couple years ago and was featured in the New York Times because of these performance features. It's designed to withstand earthquakes and floods and wildfires so that the operations of the government can continue even through these extreme events. Scott, I appreciate you bringing over to this location on campus, because the bottom photo is a structure just 2 buildings over from here. Is the Biomedical Innovations building on campus. So Stanford voluntarily designed that building to higher standards than required by regulations. And the goal is to ensure continuity of operations. It's a very active research laboratory building. There are very valuable samples that need to be refrigerated and so on. And so in both of these buildings, through careful choice of structural systems and design of elevators and stairwells and facades and mechanical equipment, that all of these things can stay functioning even under extreme circumstances, we can achieve that type of performance now. And Stanford, myself and colleagues here have really pushed a lot on developing the methods and the tools and things to do those designs. What we've seen through these voluntary projects, like the ones on the right, is that the cost premium is really only 1% or 2% on the total cost of the building to do a few targeted interventions that can really make a difference. And so taking that, or seeing that experience, building code regulators are now watching this and thinking about and actively working to pull some of these standards back into code minimums and just making this the norm in the US, which will then lead to adoption elsewhere in the world also. And so this idea of kind of designing our built environments to better performance through these extreme events is one of our big goals in our field, and an area where we're making great progress, I think. But these are one building at a time, right? And these are obviously special buildings. They're not the norm. And so the question is, what do we do thinking about these individual buildings? How do they fit into a broader community? And really the ultimate goal should be keeping our communities vibrant and resilient. And so the way we think about this and try to quantify it is through a series of staged analyses we call a kind of a probabilistic risk analysis for disasters. So we start by looking at some natural hazard process, and that's going to produce a loading intensity throughout the region that we're interested in studying. So it should be a ground shaking intensity, it could be a wind speed, an inundation depth for flooding, but whatever it is that that's getting produced by that natural process that's going to impact the environment and the assets that we want to study. Thinking about buildings, we then simulate through building damage due to that event, and these are computer models informed by experiments and field observations. And that damage then requires some amount of money and time to restore and recover from. But that's not the end of the story. When we take it to the community level, we need to think about economic activity afterwards. So this is one piece of community functioning. And we think about lost productive capital, as well as changes to demand and supply due to the changes in the physical environment of a region. We also think about household by household. How are those households impacted if they lose housing? How are they impacted if broader economic activity is impacted such that it changes their employment status? And we track through to metrics of household well-being, laying on their demographics with their built environment. And just to give you a quick example of what that looks like in terms of outputs, these were analyses for the San Francisco Bay Area. So you see a map of the bay on the left, the black line showing the Hayward Fault. This is one simulation for an earthquake on the Hayward Fault in the East Bay. And I'll step through in time kind of changes. This is changes in household consumption averaged over census tracts. And so we see immediately after the earthquake, we have this big drop in consumption as people they have to replace housing and employment disruption and so on. As we march through over time, the recovery is ongoing, and we reach back to at a macro level, kind of a similar level of economic output 3 years later in the simulation. And so you see lots of white here, but still some patches of red, particularly in the East Bay there. And you can go back and probe what's going on. These are areas that were both heavily damaged by physical damage from the earthquake, but also tend to be economically disadvantaged regions that have less resources to fund the recovery, households that tend to be more impacted by a loss in income or by some sort of financial hardship created by earthquake damage. And so you can track both the demographic and financial drivers of these impacts. And then because this is all effectively a giant digital twin of the region, you can do what-if analyses and say, if we change something in this community, what does it do in terms of the impacts? And a common finding we see is that loss of housing stock is a big driver of disruption. People in vulnerable housing that then are displaced from their homes, it creates all sorts of problems. And so you can go back and think about, what if we did targeted retrofits on vulnerable housing stock? What does that do to this whole regional simulation and the recovery time? And that's been a strategy that's been very persuasive for policymakers and has helped drive legislation to upgrade vulnerable housing stock in San Francisco and Los Angeles and other cities in California and around the world. A quick look at a second topic is this idea about designing for the future. And I'll take the flood protection problem as a quick example here. So traditionally, what we've thought about is if we're designing a flood protection system, FEMA, Army Corps will say, go look for like a 100-year flood water level, and then add a foot or two of freeboard above that. That's your design level that you need to consider. It's a pretty simple story. We can be a little more clever with probabilistic analysis and say, let's do trade-offs between the first cost of some sort of protective system versus the losses that we avoid through the presence of that system, and we can change design parameters and try to optimize for total life cycle costs. When we think about sea level rise, and we now have a moving target, the state of the art today is really to think about some sea level rise scenario. We could pick some point in time in the future or pick some level of sea level rise, and we say, let's design to have good performance under that amount of sea level rise. But that's a moving target, right? And there's a lot of uncertainty about what exactly we're going to face in 2050 or 2100. And we don't yet have a full story put together of what do we do in a probabilistic sense given that moving target. And so something that we've thought about a little bit is kind of a decision theory framing of this, where we can think through a set of mitigation alternatives that could be heights of seawalls or alternate types of strategies. We then march through into a greenhouse gas emission scenario and then a set of forecasts of sea level rise over time. And this can be probabilistic. And then for each of those sea level rise trajectories, we think out through kind of the life cycle of water elevations over a variety of tidal conditions and storm conditions. And we do simulations of damage and impacts. And this could be the regional level impact simulations like I showed you for the earthquake problem. And then you can calculate out losses and aggregate over those to think through about early designs that minimize some sort of metric. So this is a more complicated process than traditionally done, but it's got a lot of advantages. You can track uncertainties about the future explicitly. You can price in the value of adaptive solutions that allow you to come back over time and adjust the system for enhanced performance, either as you learn more or you have higher needs. You can price in the value of co-benefits, such as creating ecosystems or green spaces, or in the seawall example, we'll get seismic benefits out of the flood protection system, and you can value all of that in the financial modeling. And so there are some nice advantages in that regard. Okay, so to wrap up, I hope I've made the case that these disaster risk assessment models can be used to help design communities for resilience in the future. And I guess the way I think about the problem is if we're targeting resilient communities, what can we do backing up through all these stages of extreme events and their impacts? What can we do to change that system to help achieve these goals? Maybe on a personal note to close, I'll say, so I came to Stanford 20 years ago, really attracted by the expertise in civil engineering and geophysics here, working on these earthquake risk problems. As I sit here today and over the past year, I'm really thrilled to be a part of the Doerr School now, working with an even bigger set of experts on climate change related problems and sustainability. And I hope I've made the case that some of these perspectives and analysis methods are useful in tackling these problems. And I hope I've made the case that I could be a partner to some of you. I know there's many of you working on related problems here that interface to the types of analyses we do. And so I think engineers can really be valuable partners in tackling these types of problems, and I hope you've seen that through some of these stories today. Thank you very much.